Hi everyone. In this video I'm going to talk about VSEPR theory, which tells us about the three-dimensional shapes of molecules. Remember in the last video, which you needed to have watched before this one, Lewis structures. Lewis structures were two-dimensional representations or models of what these molecules would look like. If you were writing it on paper, what would it look like? Well, here we're thinking now 3D. For example, why does H2O bend like this, whereas CO2 is straight across? Well, VSEPR theory is going to answer that question, and it'll give us a lot of other answers as well. In order to understand VSEPR theory, which, I should define this. Well, give what the acronym is. VSEPR, I know it looks like VSEPR, but we call it VSEPR. Valence shell electron pair repulsion. Now, you don't need to memorize that. The basic idea is, the key word here is repulsion, the R. Electrons repel each other. You know that because they have like charges. And whether you're looking at water or CO2 or any other molecule, these branches, this atom here is held together with electrons. These are electrons here, and these are electrons as well. And these electrons, or electron pairs, which is the EP, electron pairs, they repel each other. So imagine you have, two arms on your body, and those arms hate one another. They repel one another. Where are your arms going to go? Everyone demonstrate this at your house. No one can see you. Be goofy. Where are your arms going to go if they repel each other? They're going to go straight out to the side. And that's what we see with the CO2. Well, here in the water, that is an electron pair. That's an electron pair. I shouldn't say whether it's single, double, triple until we actually do water. But these are electrons. These are electrons. Why don't these stick straight out? Why doesn't H2O look like CO2? Well, there's more to it than just what you see in this image here. And VSEPR theory will make it clear why water is bent and why CO2 is straight across. Let's get into VSEPR theory. So in order to understand VSEPR theory, there's just one definition we have to understand here. It's called an electron domain. An electron domain is a location with electrons around an atom. There are four types of electron domains: either a single bond, or a double bond, or a triple bond, or a lone pair of electrons. These all count as electron domains. I sometimes even call them electron regions. Here's the key. These all repel each other with equal force. Imagine we have something like SO3. So SO3, now I gave this example in the other video, so I'm going to quickly go through this. You end up getting a double bonded O, a single bonded O, and a single bonded O. How many electron domains are around this sulfur? And we only care about the central atom when we're looking at electron domains. Actually, let me finish this. We have lone pairs there, lone pairs there, lone pairs there, and no lone pairs on the sulfur. We took that lone pair away to make our double bond. Looking at the sulfur, how many electron domains do I see? Well, I see a single bond, and a double bond. That's 3 electron domains. Not 7, 3 electron domains. This does not count as 2, it counts as 1. And these are going to repel each other equally. So in reality, it's not going to look like straight across and then straight up. In reality, if your sulfate's here, we're going to have let's keep our double bond over there. Doesn't really matter where you put it. We're going to angle our single bond like that way and our other single bond this way. And I'm trying to draw this as geometrically accurate as I can, where this angle and this angle and this angle are all equal. And mathematically, you can determine that's going to be 120 degrees. Same here. So these electron pairs are going to repel each other. That's the R in VSEPR theory. And what I wrote in blue here is important. These all repel each other with equal force. It would be very logical to say, well, this one has 4 electrons, this has 2 electrons, and this has 2 electrons. So aren't these 4 gonna like repel these stronger and like kind of bend these single ones in? So it would look more like this, where it wouldn't be 120 degrees here, it would be more here and less here. That's a very logical thing to think. However, due to some much more advanced concepts than we're going to cover here in Chem 1-2, specifically something called orbital hybridization. It doesn't. It stays the same. These all repel. The double bond has equal pushing power as a single bond. A triple bond has equal pushing power as a single or a double bond. And even a lone pair has equal pushing power. What I mean by pushing power is how hard it can repel the others. They're all equal. And what did I write in red? Bonding pairs are the bonds, single bond, double bond, triple bond. Non-bonding pairs are the lone pairs. Just another vocab term. Okay, let's practice identifying the number of electron domains and whether they're bonding or non-bonding. So these are 4 examples of Lewis structures from the last video. Again, if you didn't watch that video, you have to go watch that. Here in my PF4, we're only going to look at the central atom. That's the only one we care about. How many electron domains are around this phosphorus? 1, 2, 3, 4. 3 single bonds and 1 lone pair gives us 4 electron domains, 3 of which are bonding and 1 of which is non-bonding. Looking at this, remember this was ozone, O3. Looking at the central oxygen, how many electron domains do I have here? We have a single bond, we have a lone pair, and we have a double bond. That's 3. Not 4, 3. 2 of them are bonding, 1 of them is non-bonding. Looking at my HCN, looking at the central carbon again, that's all I care about. How many electron domains do you see? 2. You have a triple bond and a single bond, just 2. And finally, my methane, my carbon tetrahydride, looking at the central carbon here, I see 1, 2, 3, 4 single bonds. That's 4 electron domains. All 4 of them are bonding, 0 lone pairs or non-bonding pairs. Same thing here. We have 2 bonding and 0 non-bonding. So let's talk about some of these actual 3D structures. So imagine we have 2 electron domains around our central atom. Both of them are bonding and none of them are lone pairs. That means we have a central atom like this. We have a single, double, or triple bond coming off one side. And we have a second single, double, or triple bond. Now, if this bonding region or bonding electron domain is going to repel the other one, where's the other one going to go? Well, this is like you with your arm sticking straight out, just like that. So one's going to go one way, one's going to go the other way. They're going to perfectly repel straight across 180 degrees. And we call this linear. Forms a straight line. Okay, now this could be a triple bond and a single bond. This could be a double bond and another double bond. And if you are going to violate the octet rule, it can be a single bond and a single bond, as long as there are no lone pairs here. And you might say, hold on, what if there's a lone pair there and a lone pair there? Wouldn't this still be linear? Because we have, sticking out one way, sticking out the other way, lone pair, lone pair. My answer to that is you're not thinking 3-dimensionally. And later on in the video, we're going to talk about why that would not be linear. So again, no lone pairs on the central atom. This is just if you have 2 electron domains, not 4. The next shape, 3 electron domains, meaning 3 bonding regions, so single, double, or triple bonds, and 0 lone pairs. So what would this look like? All right, here's our central atom, and we're going to have 3 bonds coming off of it. How are those going to arrange themselves? Well, this would be like if you had 3 arms, and their 3 arms hated each other equally. How are they going to arrange themselves? Well, one's going to go one way, the second's going to be like that, and the third's going to be like that. And I'm trying my best to draw this equally spaced out, when technically that's 120 degrees of difference, and these are equally spaced like that. Now, in reality, unless you're violating the octet rule, one of these is probably going to be a double bond. And the double bond, we talked about this before, it has the same pushing power as a single bond. It's still 120 degrees. Now, what are we going to call this shape? Well, it's a triangle shape, right? But if you think about it 3-dimensionally, it's a triangle that lies on a flat plane. So it's a triangle on a plane. We call this trigonal planar. Oops, those dots are left over from a previous draft of this video. Ignore those. Trigonal planar. It's a triangle that lies on a flat plane. Next shape, 4 electron domains. So imagine you have a central atom and 4 bonds coming off of it. Now, unless you're violating the octet rule, which does happen, what type of bonds are the 4 bonds going to be? Single bonds. So 4 single bonds. Now, if I asked you to show me how 4 branches coming off of it or 4 elements coming off of it are going to arrange themselves, most people would probably say this: up, down, left, right, like a cross shape. But you're not thinking 3-dimensionally. If you really think 3-dimensionally, there's a better way for these to space themselves out more. And in fact, we often do this with balloons. If you take 4 balloons and inflate them to like nearly full size, and then manage to tie all 4 ends together in the middle, they will naturally arrange themselves, not in a cross shape like this, but a little more spaced out, where you have your central atom, you have one thing coming off the top, I'll do it like a balloon shape, one coming off to the side, a third one kind of coming towards you. It's hard to draw here, but that's coming towards you. And then a fourth one kind of like going back away from you. Now, my artistic drawing is terrible, so I will defer to a Google image I found. And we call this shape tetrahedral. See how it's like a 3-dimensional shape? You get a better bond angle, a higher bond angle. What would this angle be? Well, that would be 90, right? 90 degrees, 90, 90, 90, 90. Well, this is a little more than that. And I forget off the top of my head, I'm going to correct myself later, but I think it's something around like 104.5 degrees. We don't need you guys to memorize that angle or anything. Just understand that these are further spaced apart than these are. And remember, VSEPR theory, valence shell electron pair repulsion theory. They're trying to repel each other as much as possible, so they're going to preferentially form this shape compared to this shape. So we call this a tetrahedral shape. And hey, remember, tetra, that's 4. Our next shape, we have 4 electron domains, but this time instead of all 4 bonding, we have 3 bonding and 1 lone pair. So what's this going to look like? Well, imagine here's my central atom. Come on, central atom. And we have 4 things coming off of this. 3 of them are bonds, 1 of them's a lone pair. Now, if I have 4 things coming off of it, it's going to resemble that tetrahedral shape, where you have 1 thing coming up, which, let me pick my lone pair as the one coming up. And then I have 1 thing off to the side. I have 1 thing kind of coming towards you out of the screen. In fact, we sometimes demonstrate that by showing it as like a triangle. You'll see that if you like Google it. And then the 4th one is like going in towards the screen away from you. And sometimes we do a dashed line to represent that. So that's my best interpretation of what this tetrahedral shape is. Let me just erase this. What this tetrahedral shape is, if these 3 were bonds and this was a lone pair. But here's the thing. In reality, you don't actually see a lone pair sticking off the top of a molecule like that. It's not really there. So let me erase it. That's what you really see. And what you really see is this shape where it's a pyramid shape with a triangular base. Okay, like think of the pyramids in Egypt. You know, they look like this, and they have a square base. Technically, it's called a square pyramid. Well, another type of pyramid would have a triangular base, which, okay, I'm not going to even try to draw this. Let's go to the Google image. So you see how this is like a pyramid shape where it's kind of bent down and you have that pyramid base underneath? Oops. That's the shape we're going to get. Now, another way of thinking about this, which makes a lot of sense, is those 3 bonds, this single bond, single bond, single bond, it would form this shape. Not that shape, this shape. It would form a trigonal planar shape if that's all that were in play. But what else is there? Well, remember, there's a lone pair, which we can represent at the top of this. Now, what's that lone pair going to do? It's going to push and bend those 3 legs down. Remember I said all the electron domains, whether they're single bonds, double bonds, triple bonds, or lone pairs, they all have equal pushing power. And that lone pair is going to push those legs down, which ends up giving you this. So there's a lone pair at the top of this, which you don't really see, bent those legs down. All right, there's one more shape. 3 electron domains, 2 of them are bonding, 1 of them is a lone pair. So what's this going to look like? All right, so we have 3 domains, 3 things coming off of the central atom. So here's my central atom. If I have 3 things, they're going to naturally be a triangle shape, right? Remember, if it were bonds, it would be like a bond, and a bond, and we called that trigonal planar. But this isn't 3 bonding pairs; it's 2 bonding pairs and 1 lone pair, like this. Now, just like before, you don't actually see that bond, that lone pair there. So that goes away. It's there, but we don't draw it, or at least it wouldn't look like it. So look at the actual shape that's left. It's like a bent line. In fact, we call this bent. So why is it bent like that? Because there's a lone pair here with equal pushing power skewing or bending those legs down. You know, if the only 2 things in play were those 2 branches, this would be linear. It would be 1 left and 1 right. But because that lone pair is there, it's going to cause these legs to bend down at even a steeper angle than that. Okay, so that's our bent shape. And I said there was one more. Technically, this is going to be the same thing drawn a little differently. 4 electron domains. 2 of them are bonding, 2 of them are lone pairs. So I have 4 domains coming out of my central atom. So in my head, I'm thinking tetrahedral again. Remember that tetrahedral? Here, I'm going to show a lone pair at the top. It doesn't really matter where you choose it. I just find it easiest to depict when I do that at the top. Let's do one of the bonding pairs coming out the side. Let's do another bonding pair kind of coming out towards us, which we can show like that. And then back here is going to be our lone pair, which sometimes is depicted like this, but then do the dots there. So we have 4 electron domains. So it almost looks like a tetrahedral, but in reality, you wouldn't actually see this lone pair or this lone pair. So notice what's actually left. The same shape as before, bent. But this time, we have a lone pair here and a lone pair there. Okay. Now, it's a lot of information. You do not need to memorize it because we have this chart that will be readily available to use whenever you need it. So this just sums up exactly what you saw in the video, where we have linear, trigonal planar, bent, tetrahedral, trigonal, pyramidal, and bent. Total electron domains, bonding pairs, non-bonding pairs. Okay, so this sums up everything you just saw before. And just so you know, there are dozens of other shapes, a lot more complicated ones that have violations of the octet rule. These are the ones we're going to focus on here in Chem 1-2. Now, moving on from VSEPR to why it all matters. Molecular polarity. Now, you watched in the first video in this unit, there's polarity of bonds, where a bond, depending on the electronegativity difference, can either be ionic, polar covalent, or nonpolar covalent. But just because a molecule has polar covalent bonds doesn't mean the molecule itself is polar. And next week, you're going to learn why whether a molecule is polar or not is so important. Here's what molecular polarity, or whether a molecule is polar or nonpolar, here's how you actually determine it. It's very simple. This is lagging on me. Come on. Drop down. There we go. You simply look at the VSEPR shape. That's it. Linear, nonpolar. Trigonal planar, nonpolar. And I'll talk about this asterisk in a sec. You see where I'm going with this. Bent, polar. Tetrahedral, nonpolar. Trigonal pyramidal, polar. Bent, polar. Now, before I address this asterisk here, look at the image here and the molecular polarity. And I'm curious if anyone can figure out what makes something polar or nonpolar. It's not random. What do you notice about the 3 that say polar that aren't on the ones that say nonpolar? The answer is these dots. See the lone pair? See the lone pair? See the 2 lone pairs? When the central atom has lone pairs, unbonded electrons, it throws off the symmetry of the molecule, and it kind of skews that molecule. I almost said the word bends that molecule, which it does in really. It skews, or I could say bends. It bends that molecule, which gives it the polarity. If there are no lone pairs on the central atom, like this one, or this one, or this one, no lone pairs, that makes it nonpolar. As long as the branches are the same element. Now, this term branch is not a chemistry term. I just threw that in there. What I mean is the things coming off of it. So, for example, tetrahedral shape, this one. So if you have a carbon with 4 bromines coming off of it, Br, 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 Br. Even if the carbon-bromine bond is polar covalent, which I'm trying to think off the top of my head, electronegativity values. I think this one is, I think bromine's 2.8 and carbon's 2.5. So I think that's technically non-polar covalent. Here, even more extreme example. Fluorine. Hold on. Fluorine, electronegativity, the 4.0 GPa of the periodic table. So the carbon-fluorine bond is very polar because carbon's 2.5, fluorine is 4.0. That's a huge polar value. However, because it is pulling perfectly evenly, it cancels out. This would be like, imagine a tug of war with 4 teams pulling on the same thing in the middle, and each team is perfectly equally strong. That center point's not actually going anywhere. It's perfectly balanced, and for this reason, the entire thing is nonpolar. Now, if we threw this off a little bit, and all of a sudden 3 of them were fluorines, and 1 of them was an iodine, well, now they're no longer equal strength, because the electronegativity difference here is going to be different from the other 3. This will end up being slightly polar. So as long as the branches are the same element, it will be nonpolar, even if it has polar bonds. So all you need to look at is the VSEPR shape, just to drive this point home. Molecular polarity, or nonpolarity, meaning whether a molecule is polar or nonpolar, depends only on the VSEPR shape, not the type of bonds between the atoms, meaning whether they're polar covalent or nonpolar covalent. The second line here, I just summed it up on the last slide. If the VSEPR shape is symmetrical, meaning no lone pairs, what are the symmetrical ones? This one is symmetrical. This one is symmetrical. This one is symmetrical. No lone pairs. If the VSEPR shape is symmetrical, the bond polarity cancels out and the entire molecule is nonpolar. Asterisk, as long as the branches are the same element. All right, so let's go through some quick examples and talk about the VSEPR shape and whether or not it's polar. Okay, so I went and recopied all the Lewis structures from the last video, so none of these have to be done out, and make sure you understand those. So the first one is O2. Now, whenever you have 2 elements, there's only one thing it could possibly be. It has to be a straight line. In fact, it doesn't even match this because this linear requires 3. Any kind of 2 elements is always going to be just linear. Let me write that a little more clean. Linear. Now, is this going to be polar or nonpolar? Well, in linear, these are pulling perfectly across, and really these are the same element. As long as it's the same element, it's perfectly evenly balanced. This one's going to be nonpolar. Nonpolar. So linear is nonpolar as long as it's the same element. CH4. Okay. How many electron domains do we have here? 1, 2, 3, 4 electron domains. So it's going to be one of these. How many of them are bonding pairs? All 4 of them. How many non-bonding pairs? 0. What shape? Tetrahedral. So methane forms a tetrahedral shape. So in reality, it's not going to look like a cross. It's going to look like, I've tried to draw this a bunch of times, like that, and then this one kind of sticks out towards you, and this one kind of goes into the page like that. Okay. Now the CH bond is slightly polar. However, because it's tetrahedral, because there are no lone pairs on the central atom, it cancels out. This is going to be a nonpolar molecule. Nonpolar. Because there are no lone pairs on the central atom, because it's symmetrical. PF3, phosphorus trifluoride. So here's our Lewis structure. How many electron domains? 4. So it's one of these. How many of them are bonding? 3. How many non-bonding? Right there, 1. This is going to be a trigonal pyramidal shape, just like in that little picture there. That lone pair skews down the 3 fluorines. If that weren't there, it would be trigonal planar. It would look like this one, but the presence of the lone pair on that central atom pushes those legs down. Is this polar or nonpolar? I don't care about this. I don't care about this. I don't care about this. All I care about is that lone pair. There's a lone pair on there, which makes this polar. Okay, so it's trigonal, pyramidal, and polar. SO3. How many electron domains? 1, 2, 3, 4. 4 electron domains. I've been doing this way too many times and my head's starting to go crazy. That is not 4, that is 3. The double bond counts as 1. 3 electron domains, which means we are one of these 2. How many of them are bonding? All 3 of them. How many lone pairs? 0. This one is a trigonal planar shape. So in reality, it's not really going to look like this. It's going to look more like SOOO, kind of like that. Is this polar or nonpolar? Well, there are no lone pairs on the central sulfur. This is going to be a non-polar molecule. Even if there is, and there is, the SO bond is quite polar, it doesn't matter. It cancels out. This is a non-polar molecule. Br2. This is 2 elements are the same. This has to be linear. And this is going to be non-polar because it's the same element. HCN. Looking at the central carbon, how many electron domains do we see here? 1, 2. Just 2. Both of them are bonding pairs. No lone pairs. This is linear. Linear. Now, is this polar or non-polar? I don't see any lone pairs here, but hold on, careful. Remember, this is that asterisk exception. The H is on one side, the N is on the other. So this would be like if you're bench pressing, but you have different weights on the left side and the right side. That would be very hard to bench press. You know, it would be all skewing up and down. So this is going to be linear. However, because it's different branches, this is going to be polar. All right, SiCl4. So we have 1, 2, 3, 4 electron domains. So it's going to be one of these. All 4 of them are bonds. No lone pairs. This is tetrahedral. No lone pairs in the middle makes it nonpolar. Simple as that. Nonpolar. All right, and so we've done this type of thing a bunch. This is going to be linear. Doesn't matter that there's a triple bond. And because it's the same element, this is going to be nonpolar as well. O3, which is ozone. All right, let's count our electron domains. 1, 2, 3. 3 electron domains, so it's going to be one of these. 2 of them are bonding. 1 of them is non-bonding. Here's my 2 bonding, my 1 non-bonding. That's bent. Bent like this. So in reality, it's going to look sort of like that. All right, now for polarity. This one's really interesting. What's the electronegativity difference between this O and this O? 0. What's the electronegativity difference between this O and this O? 0. There is no electronegativity difference. However, this one is still polar. Why is it still polar even though there's no difference? Because of the bent shape. These lone electrons throw off the symmetry of this molecule and make it polar. Again, it all has to do with the VSEPR shape. It doesn't have to do with, you know, doing the 3.5 minus 3.5 giving you 0. All right, CH3F. So here's my central carbon. We have 1, 2, 3, 4 electron domains coming off of it, which means we are one of these. All 4 of those are bonds, meaning this. 0 non-bonding pairs, that's a tetrahedral shape. Is this polar or non-polar? Well, notice 3 branches are hydrogens, 1 is fluorine. This is one of those exceptions where this will end up being polar only because it's not all 4 branches. Okay, so these are all the ones from the last video. I'm just going to take a few minutes and very quickly run through a few more examples of some VSEPR shapes. I think I duplicated that. All right, so these are the 5 I'm going to do. If you want, you should pause this video now, work out the Lewis structures, tell the VSEPR shape, and indicate whether it's polar or nonpolar based on that. All right, I'll go through them now. CBR4. Now I'm going to go fast through the Lewis structures because the other video goes through it slowly. So I'm assuming you guys know how to do these. So carbon with 4 bromines. Each bromine gets lone pairs. Like this. Central carbon, no lone pairs. Let's count. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. That's 32. Carbon on the periodic table has 4. Bromine has 7 times 4 is 28. 4 plus 28 is 32, which means this is, in fact, the correct Lewis structure. Okay, if it's a Lewis structure, let's find the VSEPR shape. So we have 1, 2, 3, 4 bonding regions, or I should say 4 electron domains, all 4 of which are bonding pairs. 4 electron domains, 4 bonding pairs, no lone pairs. This is a tetrahedral shape. Tetrahedral is nonpolar as long as all 4 branches are the same. Notice no lone pairs. All 4 branches are the same, therefore carbon tetrabromide is nonpolar. Next example. Oops. NH3, you know that as ammonia, not ammonium, ammonia. All right, central nitrogen, 3 hydrogens coming off of it. Lone pair around my N, but not around my H's. Remember, no extra pairs around hydrogen. All right, let's count. 2, 4, 6, 8. That's 8 electrons there. N is 5. H is 1 times 3 is 3. 3. That gives us 8. Notice the numbers match. That means that this is the correct Lewis structure. Now let's tell what the shape is. We have 1, 2, 3, 4 electron domains around the ammonia, meaning it's one of these. 3 of them are bonding pairs. 1 of them is a non-bonding pair. This is a trigonal pyramidal shape. Trigonal pyramidal. Is this polar or non-polar? Well, the presence of that lone pair right there tells us this is polar. Polar molecule. BF3. Now this will be an octet rule violation. Should have clarified that before. BF3. So it's going to look like this. Okay. Now boron. Well, let me count these first. So we need pairs around the fluorines. And here's a violation, which you wouldn't know about unless I told you otherwise. Boron does not require an extra pair down here. It happens to be more stable without it. So boron's violating the octet rule with only 6 there. So that's going to be our skeleton right there. No pair at the bottom. Okay, so for BF3, boron is, I'm blanking on my periodic table location for boron. I think it's 5. No, it's 3. 3 valence electrons. Fluorine is 7 times 3 is 21. That equals 24. Let's count the dots here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So again, we are good. No need for double bonds yet. Let's check our VSEPR shape. So looking at the central atom, we have 3 electron domains. So it's going to be one of these. 3 of them are bonds. No non-bonding pairs. This one's going to be a trigonal planar shape. So in reality, this is going to kind of skew off so it's perfectly balanced with the others. Is this polar or non-polar? Well, there are no lone pairs on the boron in the middle. That makes this non-polar. Okay, just a couple more. CO2. Carbon goes in the middle. Oxygen on one side. Oxygen on the other side. We need dots around these atoms like so. Let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Carbon is 4. Oxygen is 6 times 2 is 12. 4 plus 12 is 16. We are off by 4. You can probably tell where we're going to go with this. Well, we can make a double bond, which we'll do here. Oops, double bond. That'll bring us down to 18. We're still not there. We need to make one more bond. Now, theoretically, you could chop another 2 and 2 and make a triple bond, but it's not really going to be stable with a triple bond on one side and a single bond on the other. You know, it'd be like if you're trying to bench press weights, if you're trying to bench press 100 pounds, you're not going to put 75 on one and 25 on the other. You're going to do 50 and 50. Same thing in this VSEPR. We're going to go from the other side, take 2 off there and 2 off there, give us our double bond here. And now that brings us to 16, 2, 4, 6, 8, 10, 12, 14, 16, and we're good. All right, let's find the VSEPR shape. So CO2, we have 1, 2 electron domains. Both of them are bonding pairs, no lone pairs. This is linear. Okay, is this polar or nonpolar? Well, there are no lone pairs on the central atom. These are the same thing. This is going to be nonpolar. Even though the CO bond is quite polar, they cancel out. CO2 ends up being nonpolar. All right, last one. May as well end on the one that you are most familiar with, water. All right, Lewis structure for water. O in the middle, H on one side, H on the other side. Lone pairs not on the H's, but yes on the oxygen. Let's count. 2, 4, 6, 8. 8. Here, with the periodic table, hydrogen is 1. That gives us 2. Plus O is 6. 2 plus 6 is 8. That means that, yes, this is the correct Lewis structure for water. Now, let's find the VSEPR shape. How many electron domains on that oxygen? 1, 2, 3, 4 electron domains. So it's going to be one of these. 2 of them are bonding pairs. 2 of them are lone pairs. Notice the bent shape. Now, you already knew that about water. You knew that water was bent. Probably when you came into chemistry, you knew it was bent. Now you finally really know why. Why is water bent and not linear? Because if you look at this and say, what shape is that going to be? You might say, well, it's going to be linear, straight across, and then just the dots on the top and the dots on the bottom. But in reality, the water is going to have a central oxygen, and it's going to have 4 things coming off of it. And whenever 4 things come off of it, they don't go in a cross shape. It goes 1 up, like a hydrogen, 1 to the down in the side, like another hydrogen, 1 coming out towards you, like a lone pair, and 1 going kind of into the page, like another lone pair. So you see how it's that tetrahedral shape? But in reality, you don't really see those lone pairs. All you really see is this. And that's why your water is bent. Very important. In the next video, you're going to talk about, or in the next unit, you're going to see why the polarity is so important. Oh, I kind of skipped ahead. Is this polar or non-polar? Well, you already knew that water was polar. Now you know why. Why is it polar? Lone pairs on the central oxygen make it polar. Usually in this unit, I ask my students, why are we here? As if I'm being all metaphysical and all that. Why are we here? And what I mean by that is why are we in a classroom? How have we evolved to be where we are? Where did this all start? And my answer is these lone pairs. It all started with those lone pairs. How? If it weren't for those lone pairs, if those lone pairs weren't there, like imagine it were double bonded hydrogens, which you can never have. Water would look like this. Okay? Water would be nonpolar. Now, next week, you're going to learn that something being polar means it has a very high melting and boiling point compared to something nonpolar. That's why CO2 turns into a gas at -86 and H2O turns into a gas at 100. If water were nonpolar, we would not have liquid oceans. If we didn't have liquid oceans, we would never have life forming 3 billion years ago. If we never had life forming 3 billion years ago, we would not be here. So why are we here? Because the lone pairs on the water bend the water's structure. That bending gives water polarity. That polarity leads to its high melting and boiling points, which leads to liquid water. And once you have liquid water and all the right ingredients, you have life. So that's why we're here. All right, thank you for paying attention to this video. Good luck, of course, see your teachers in Zoom.